So in chapter 15.7, we're going to be introducing yet two more different coordinate systems. So we've already built up two so far, right? We know from early high school, we've used the, the rectangular coordinate system. So we had rectangular, and then 2 lessons ago, we added to that the polar coordinate system, and now we're adding 2 more. So the cylindrical and spherical are just 2 more types of coordinate systems. And again, to reiterate, the reason why we're doing this is not to make your life more difficult, but in fact, it'll be much easier to evaluate integrals in these different coordinate systems if we know when to appropriately apply them. So let's first take a look at the cylindrical coordinate system. It's a little bit easier and more intuitive. The variables that are in it are 3. There are 3 variables in cylindrical. There are r, theta, and z. So if you notice, this is made up of 3 components. So there's 3 different variables, which means that this coordinate system spans R3. So it's a 3D coordinate system. And it actually might look familiar because this portion of the cylindrical coordinate system is really just polar, right? So r and theta, right, for the first 2 components is the polar coordinate system with a z component attached to it. And it's just your regular Cartesian z, so just a straight z height. So really all that cylindrical coordinates are is it's your polar system here on the xy plane. Remember, polar was just a 2D coordinate system where you add in a z value, right? So now you can expand it to all of R3. You can get to any point in 3D by just rotating in the polar coordinate system to your point on the xy plane, so getting underneath the point and then going directly straight up. Right, so if you remember, this theta is still an angle measured from the positive x-axis. R is the radius from the origin, or remember we call this the pole when we're using a polar coordinate system. And then you're just adding in a regular Cartesian z height. Right, so it's pretty intuitive. And the reason why we call this a cylindrical coordinate system is because you could imagine that if you leave r constant and z constant, and you just let theta vary around, so you vary theta throughout its entire range from 0 to 2 pi, you would trace out, or you could trace out this kind of cylindrical shape, right? So it's really good. Let me make a note of this. So the cylindrical coordinate system, right, is good for describing cylinders. Right, especially when the sides of your region, when the sides of the region, the sides of the region you're integrating through are cylindrical. Right, because this idea that letting r and z stay constant and just varying theta, it traces out this nice cylindrical side. So we're going to see the cases when it's good to use a cylindrical coordinate system to integrate through a 3D space. Right, so these are used for integrating triple integrals. Because it is a 3D coordinate system. So when you see that your region D, right, so when D is cylindrical in nature on the sides, then it's a good idea to convert to a cylindrical coordinate system. And so that's when you would need to use your conversion equations. Right, so let's get the conversion equation. Here's the conversion equation for rectangular to cylindrical. So we have one for x, y, and z. So x, right, and remember the first 2 components in the cylindrical coordinate system are polar. So it's going to be the exact same conversion equation. So x will still be r cosine theta. Y becomes r sine theta. And then remember, this z is just a regular Cartesian z. There's no conversion. So z is just the same z that you've been using from before. So z is z. And now let's get what the volume differential becomes. So your dv So the volume differential in that dv, which is usually like dx, dy, dz, right? You can probably guess what this comes. We'll first do dz. So dz is just the same because z is z. And now, remember, your next two components are just the polar coordinate system. So you're just going to do the polar differential now, which is just r, dr, d theta. So dv in cylindrical becomes dz times r times dr d theta. Pretty straightforward. So that's the cylindrical coordinate system. And now we're going to introduce a second one. Right, so this is now our fourth coordinate system that we know, and that's the spherical coordinate system. And so this one, let me match the colors. Yeah, darker blue. So spherical coordinates, these are good for a couple different applications. So they're good for describing, obviously, spheres, or parts of spheres, like hemispheres or quarters of spheres. As well as cones. We'll see why they're good for cones. And what I'm going to call the bundt cake shape. And you'll see what that shape is. Here, it's really a hemisphere with a cone taken out of the center, right? And so I call it the bundt cake shape, and it actually appears quite a bit when we're working in integrating through 3D regions. So those are the conditions or the situations where you see your region of integration. Those are the ones where you would want to use a spherical coordinate system. And so the variables that are in spherical coordinates, I'll do these in green. So it is a 3D coordinate system, right? It's a 3D system. So we know we need to have at least 3 variables. And in this case, the variables for the variables for a spherical coordinate system are rho, right? The Greek letter rho, phi, and theta. Right, so these are 3 new variables that we kind of haven't seen before. And so we'll talk about each one individually. So first we have rho. And this is the Greek letter R, right? So this is rho, which is Greek R, and we use that because it is a radius. So it's a radius from the origin in 3D. Right, so it's just like R in polar, except we use rho to specify the fact that now that R is not just in the 2D plane, but it can be in 3D. So it's just a radius from the center, and you can see that here. So from the origin to your point, right, it's just a 3-dimensional radius to your point. So there's the first variable. 1. Secondly, we have phi. Let me do that a little bit better. And this is another Greek letter. And this is another angle. So phi is an angle that is measured from the positive z-axis. Right, so this is different. We haven't seen anything like this before. So phi actually measures not from where we're used to measuring, right? We're used to measuring angles from the positive x-axis. In this case, phi is a measure from the positive z-axis. So here's the positive z-axis, and this phi angle is measuring up there. This is also called the zenith angle. If you know anything about astronomy, the zenith is looking straight up into the sky. So this is an angle away from the zenith, or the top of the plane. Right? So you're measuring from the positive z-axis. So that's important to keep in mind. And then thirdly, the third variable we have is theta. And theta is just like we've been used to from before. It's another angle from the positive x-axis. So this is exactly the same theta from polar that we saw 2 sections ago. So it's an angle from the positive x-axis. Right, and so you can see as well that it is just the same theta from the positive x-axis. And so what this spherical coordinate system is saying, it's saying that any point in space, let me pick a contrasting color, Let me do like this orange. So any point in space, say P, can be represented with the combination of one length, the length given by rho, so rho is a length from the origin, and two different angles. So the combination of a length and an angle from the positive x-axis and an angle from the positive z-axis. And so those three together are able to span all of our three and get any point in space. But they're especially nice for, like I said, describing spheres, parts of spheres, cones, and that specific bundt cake shape that we'll look at here in a second. So let's take a look at the conversion equations. So how do we convert between rectangular and spherical coordinates? Now these conversion equations, we're not going to derive them. They're a little complicated. You can derive them. They're all just based on similar triangles. So you can do that as an exercise on your own, but I'm just going to list them out here. So from rectangular to spherical. So from rectangular to spherical. Here are the conversion equations, right? It's a 3D coordinate system, so we'll need three. One for x, one for y, and one for z. So x in spherical becomes rho sine phi cosine theta. Y becomes rho sine phi sine theta. And z becomes rho cosine phi. Okay, so we're not going to worry about exactly where those come from. Like I said, you can derive them on your own pretty easily. They are a little bit more complicated than the other conversion equations we have, so you're not going to be asked to call on those super often, but it is just to know that they do exist and just have an idea of what they are. But importantly, we do need to know what the volume differential becomes. Right, so when we integrate through a 3D region using spherical coordinates, we have to have that volume differential at the end. So we need to know what that becomes in spherical. So the volume differential in spherical, right, so the dV becomes, right, so we have three variables. We'll have d rho, d phi, d theta. So d rho, d phi, d theta. But you remember when we were in polar, we talked about that there was an extra r that got multiplied in there into the volume differential, and we weren't going to worry about it right away, but we'll discover it in chapter 15.8. There's another factor that gets multiplied into the spherical volume differential that we're going to learn where that comes from in the next chapter. But just for now, know that that extra multiplier in spherical is rho squared sine phi. So anytime you convert to spherical and you're integrating, dV becomes rho squared sine phi d rho d phi d theta. Right? And so this rho squared sine phi can just get multiplied into the function you're integrating, just like any other constants or variables. So they just become things that you're integrating as well. Okay, cool. So let's look at a couple questions and problems that are going to further explore these two coordinate systems. Okay, number 14. So here is an integral. It looks like it's written in Cartesian coordinates, right? X squareds, dx, dy, dz, right? So I know that this is in a rectangular coordinate system. So now we need to convert this into an equivalent integral in a cylindrical coordinate system and then evaluate the result. So the first thing I'm going to do is I'll probably do a little sketch of what's going on here. So let me sketch out D. Right, so D is that region of integration. So I'm just going to sketch out the region real quick, just so we get an idea. This isn't required. You could just use the conversion equations to get it, but I think it's nice to get a little picture and a visual of what's going on. So in the z direction, we're going from 0 to the equation z equals x. Right, which is just your 45-degree line on the xz plane. So it looks like on the xz plane, we're here, so there's going to be, it looks like something that looks like this. Right, so you would imagine that this line right here, oh no, where did it go? So this line right here is the line z equals x, and it's on it lies on this xz plane, right? So you kind of have to force the perspective to work, but that's where that line lives. And then in the x direction, we're going from 0 to x equals the square root of 1 minus y squared. And we talked about this a couple sections ago. That's our semicircle on the positive x portion, right? So where x is positive, right? That's going to be a circle of radius 1. So it's kind of going to lie there like that, right? Let me draw the negative portion of the y-axis as well. Okay, cool. So that right there is the, what is this? This is x equals the square root of 1 minus y squared, right? In the negative version, the negative square root of 1 minus y squared, that would trace out the back half of that unit circle. And then in the y direction, we're just going from negative 1 to 1, which is already where this goes, negative 1 to 1. Okay, so what this shape looks like is it is going to look like this cylinder kind of extending up, this half cylinder, right? But it's going to be cut along the top, along this z equals x line, so this 45-degree angle line, right? So it's going to, it's kind of a tricky shape to draw. So you can imagine if there's this plane cutting this half cylinder in this direction. So let me try my best to draw what this shape would look like. It would kind of look like, not that this is even super critical to understand, but it kind of is interesting nonetheless. So you have, this is going to be hard. Yeah, it is. It's going to kind of look like a shape like this. So it's kind of this wedge shape that's, there we go. Ooh, that's probably my best drawing. So this is D. That is the volume you're integrating. And you can imagine it's just turned around to face, so that this is the y-axis. This is the x-axis. And this is the z-axis. So I just drew it from a different perspective, so it's a little easier to see. Okay, so that's all that this is. Whoop. So that's our volume that we're integrating. Now let's convert that into cylindrical coordinates. So we'll set up another integral. Our function in this case is x squared plus y squared, and we know that in cylindrical coordinates, x squared plus y squared, just like polar, becomes r squared. So we're integrating r squared, and we have dz, r, dr, d theta, and then our bounds. So the bounds in the z direction, z is just z, right? So z doesn't change. So in this case, it looks like we'll still be going from z equals 0 to z equals x, right? And so x becomes r cosine theta in spherical coordinates. So we'll have 0 to r cosine theta. And then the radius, right? So now in r, let me pick a different color. So r still goes from 0 to 1, right? So that's r equals 1. So we know here we're still going from 0 to 1. And then for, what is the last one? Oh, for theta. Yeah, theta will go from, right, this is theta equals 0. Out here, theta will go from negative pi halves to pi halves, right? The negative y-axis to the positive y-axis. So it's negative pi halves to pi halves. Okay, cool. So that's the setup we're going for. What we can do is we can distribute that extra r into the function that we're integrating and just call it r cubed. Right, so that's totally valid to do. Yeah, so that's the setup. I'll let you evaluate this on your own. So evaluate that integral on your own, and the answer that you should be looking for is 2/5. So that, in this case, would be, that's the answer to that integral. Okay, let's look at number 15. Number 15. So D is the right circular cylinder. So I see the word cylinder, so I know we're probably going to be using a cylindrical coordinate system whose base is the circle r equals 2 sine theta. All right, so 2 sine theta is that is going to be a circle of radius 1 that has been shifted 1 unit up. All right, so its center is going to be at 0, 1. All right, so that's 0, 1. So that's the base of it in the xy plane, whose top lies, so the top is cut by this plane, z equals 4 minus y. And so z equals 4 minus y is this plane up there. Right, so that's kind of cutting the top, and you get this kind of, this is like a lipstick tube kind of shape. And this is a really common one for spherical coordinates because it is just a cylinder with an irregular top described in z. Right, so this should be pretty easy to set up. So all we're going to do is I'm going to set up an integral to find the volume of it. So let me get my triple integral. So the volume of this region will be the triple integral of 1, right? If we're trying to find the volume, we're just going to integrate 1. dv becomes dz r dr d theta. So let's do the z bounds. Z will go, we're starting at the xy plane, so z starts at 0 and goes to z equals 4 minus y, right? But y in cylindrical becomes 4 minus r sine theta. So that's our top. In r is given to us. R is variable, but the variable equation was already given to us. So it goes from 0 to this kind of equation given by r 2 sine theta. All right, so that's pretty easy. So from 0 to 2 sine theta. And then for our angle theta will go from 0, right, because we start there, and we go all the way around to pi. Right, so it's from 0 to pi. And that will give us that whole lipstick type region. Okay, so that's how we calculate the volume. So those were two examples of using spherical coordinate, I keep saying spherical. Those were cylindrical coordinate problems. Now let's transition to looking at a couple spherical coordinates. So in example 2, all we're asked to do is identify the surface for each of the following equations, right? So we're identifying some kind of surface. And what this exercise is really doing is it's showing you the unique properties of the variables that make up the spherical coordinate system. And so what this is saying is if I was just given the information, if I was just given rho equals 5, what shape is that? So here, let's come over here. So for letter A, for rho equals 5, let's go back up to our picture of the spherical coordinate system. So you're just setting rho to be a constant, and you're letting the other two variables vary. So if you were just doing a constant 5, and you let it go everywhere else, that would actually trace out a sphere of radius 5. Right, so the equation rho equals 5 in spherical coordinate systems that's a sphere with radius 5. Right, so that would just look like, that's just a sphere of radius 5. Whoop. There we go. So that's rho equals 5. Easy peasy. Now let's look at B. So B is phi equals pi thirds. Okay, let's go back up to our drawing real quick, because it's easier to explain with this guy. So if we now we're letting phi be constant. Right, so this angle doesn't change, but instead we can get longer and shorter and sweep around this way. All right, so what shape is that going to trace out? If we let this angle stay constant, that's actually going to trace out this shape. Right, because all around and in every, like this could extend out infinitely wide, that's going to create a cone. And so that was one of the things that we said that spherical coordinates were good for describing, cones. And that is because if you let phi be constant, it is a cone with that angle. So in this case, phi equals pi thirds, that is a cone with an internal angle equal to pi thirds. So a little drawing of that surface would be like this. So here's a cone where that angle is phi. Okay, sweet. Now let's look at letter C. So for letter C, C is just theta equals 2 pi thirds. Now, take a moment on your own to think about what the resultant surface would be if you let theta be constant. So a constant theta, but instead you can vary phi and rho. So you can get wider and you can get farther and closer to the origin, and you can sweep up and down from the z-axis. So the shape that actually makes is if you let theta be constant, then that's going to be a plane. Like this. This is the half plane. So it's a half plane extending from the origin out in the direction of theta. Right, where that's theta. And so when you let theta be constant, the result is what's called a half plane. So the resultant surface from theta equals 2 pi thirds is a half plane. That would look like, let's see if I can just copy this. Copy, paste, very nice. And so if we say that this is the x-axis, 2 pi thirds, where would that live? Let's just say it's pi thirds, just for drawing's sake. So pi thirds would be kind of like this angle, and then this would be the half plane. Right, and it extends infinitely. Right, it extends this way and this way, right? But it's kind of this plane extending out at an angle of, in this case, it would be like pi thirds. And 2 pi thirds would just be the one pointing in quadrant 2. Okay, beautiful. So those are 3 different surfaces that you can get from setting each of the spherical coordinate system variables equal to constants. So there are 3 surfaces you get by setting spherical coordinates, there are spherical variables, constant. So that's kind of the idea that this problem was getting at. Okay, let's take a look at number 49. So spheres and cones. Spheres and cones. Find the volume. Finding volume, that's a good indication that we're going to be using a triple integral, of the portion of the solid sphere. Rho is less than or equal to a, so this again is that variable radius, so we're finding a general equation for volume that lies between the cones, phi equals pi thirds, and phi equals 2 pi thirds. All right, so those were these types of cones. Remember, setting phi equal to a constant gives you a cone. So let's again draw a sketch of what this shape is. Spheres and cones. Okay, so this will be x, y, and z. So we're finding the volume of the portion between, okay, so the sphere, so I'll do the sphere in red. So this is just going to be a sphere centered at the origin of radius a. It's less than or equal to, so it just means it's filled in. It's not just the surface, but it's like the entire shape. So it's kind of solid, not hollow. So let's say that it looks something like that and that. Whoa, that was very bad. Actually, if I do a small one, I can blow it up. And then like this. There we go. Okay, so I'll just select these. Whoa, look, the iPad is great. So this is, what was it? Rho is less than or equal to A. Right, where that A could be any radius. And then it's lying between the cones, pi thirds. So I'll do this one in green. So remember, phi measures from the positive z-axis. So we'll go from the positive z-axis down pi thirds. So here's one cone. And then I'll do the other cone in blue. 2 pi thirds. So 2 pi thirds is past pi. Phi equals pi is the positive x-axis, right? And so 2 pi thirds would be the symmetrical cone pointing downwards. So it would be kind of like this guy. So that is phi equals 2 pi thirds. So the shape we're trying to find the volume of looks a little bit like this. So D is kind of this shape. If you can imagine this, where on the inside there are these two cones that converge at the origin, right? So they're hollow. So it almost kind of looks like a bead, maybe, right? You could run like a piece of string through there. So yeah, that's the shape we're trying to find the volume of, and this will be pretty easy to set up an integral for. So we'll do a triple integral. Here we go. 1, 2, 3. We are in spherical coordinates, so the volume differential becomes rho squared sine phi d rho d phi d theta. And then our bounds for rho, in this case, are from 0 to A. For phi, they are from, right, so we enter at pi thirds and exit at 2 pi thirds. So it's just from pi thirds to 2 pi thirds. And then for theta, right, it's symmetrical around the z-axis, and we want to capture the entire thing, so it'll just be from 0 to 2 pi. There we go. And so that will give you the volume of that shape. The answer you're looking for when you evaluate it on your own is 2 pi a cubed divided by 3. All right, and so what this general equation is saying is, it's saying that this bead could be of any radius. So it could get bigger or smaller, right? But the equation for finding the volume of it will be the same. Right? So you just plug in whatever that radius is. Cool, so that's what we found. Number 33. Whoop, too far. So this one is asking, it's missing the question again, but I'll just add it. So find the volume of the solid between the sphere rho equals cosine theta, which is this sphere right here. And it's really helpful because it's giving you a picture. I don't think you would be expected to know what that shape looks like, right? So you don't need to know this. So you don't need to visualize it. That's why a picture was given. So yeah, whatever. In the hemisphere, rho equals 2, which is this outer one here. That's rho equals 2 is this hemisphere. And z is greater than or equal to 0 just means it has to be above the xy plane. So that's what makes it a hemisphere. So we have this smaller sphere, rho equals cosine of phi, and then this bigger one, which is just rho equals 2, and we're cutting it off at the top. So we're trying to find the volume of it. Let's do it over here. So the volume of this shape is going to be a triple integral. of 1 rho squared sine phi d rho d phi d theta, and then our bounds for rho. So rho, you can imagine we're trying to find the volume in between these two shapes, right? So we don't want to be in the region at the origin, right? At the origin, you're not in the region until you get to this this first bound. So the initial rho is rho equals cosine phi. So you enter the region there. So yeah, you're entering at cosine phi, and you're exiting at rho equals 2. So that took care of the rho bounds. Phi goes from 0, right? So up here is 0. That's phi equals 0. And you're going all the way down to the xy plane, which is a 90 degree turn, which corresponds to an angle of pi halves. Right, you kind of have to shift your perspective when you're working in spherical, because we're not used to measuring angles from the positive z-axis when doing phi. So you really do have to remember to kind of shift your thinking a little bit. But now when you're on the xy plane, that is phi equals pi halves. So it's from 0, let me get consistent with my color, from 0 to pi halves. And then for theta is just from 0 to 2 pi to get the entire circular shape. So from 0 to 2 pi. Oops, let me clean that up. From 0 to 2 pi. And so evaluating that integral will give you the volume of that hemisphere with a little circle taken out of it. Again, I'm not going to go through the evaluation because these are techniques that you should definitely know on your own. But just for your reference, the answer you're looking for to give you the volume of this region is going to be, let me make sure I give you the right one. It should be 31 pi over 6.